Hi there, Science 9. So what we're going to do just now is the lesson for, in fact, lessons 7 and 8, the water cycle and the carbon cycle. I'm going to do them at once. I just like to get through all of these cycles to be done this notes package. That way you'll all be able to most effectively write up your nutrient cycling project, which I know is I've made due fairly soon. Some of you have already finished it. That's great. If you haven't and you're looking for a little bit of guidance, you'll have this, the other lesson, and I'm going to shoot you an email as well pretty soon. So I'm going to start with the water cycle. So I know I like to, this is kind of becoming old school with my screen lessons, but here's what my drawing is, kind of a conventional drawing of the water cycle. We have a body of water. Next to it are some mountains, and we've got processes that happen to water. One, where water turns from a liquid to a gas, evaporation, and it goes into the atmosphere. The second, which would be condensation, which is the opposite, where it goes back into a liquid. When the droplets get big enough in the air, they form raindrops and fall as precipitation, rain or snow. Some of that water, however, doesn't go directly back down to the ocean. Some of it falls on the land. All the water that falls on the land, some of it ends up just flowing on the surface. Some of it ends up in fresh water bodies, and some of it ends up as groundwater. Now, of the water that ends up in groundwater, of the water that ends up in land, some of it will end up in vegetation. So that vegetation can then take up the water. We're talking generally here of like terrestrial plants that have roots. They bring the water up through the plants and they become part of the plant itself as the plant grows and turns carbon dioxide and water into sugars, which makes the plant bigger. So that's how the water enters living things, and then of course from there the water can become part of food chains when organisms eat plants, and then water can return from there back into the air. Another way that could happen, though, by the way, is when plants with roots are taking in water, it goes up through the shoots, and then most of it comes out of the leaves. So basically the plant is like a giant straw, like a tree is like a giant straw, sucking water out of the ground and then just sending that water into the atmosphere. Yeah, some of it gets used for making sugars, which is what the plant does to feed itself, but some of it is used for transpiration, which helps the plant stay upright. So that's a bit about the water cycle. I'm going to show you a little bit more about the water cycle in the screen lesson part of this here, going through some of these key points and definitions, making sure you have all those terms down. That being said, I'm thinking in elementary school, probably a whole bunch of you have already encountered the water cycle. Hi there, I got interrupted there. So continuing with the carbon cycle. The carbon cycle is different from the water cycle in one really important way, in that within the carbon cycle, carbon takes a lot of different forms chemically. It changes chemically a lot more. Within the water cycle, yes, some water becomes part of the sugars that are in plants, but within the carbon cycle, yeah, carbon is in the atmosphere as carbon dioxide. Within plants, it becomes locked into the sugars. It's a plant molecule called cellulose. Some of those sugars enter food chains and become other compounds that have carbon in them. Some of the carbon gets locked into the soil. Sometimes it's just charcoal, like elemental carbon. Some other carbon goes into fossil fuels, and then it's a different kind of carbon molecule. Some of it ends up in coral and in shellfish, and that's another kind of carbon-containing molecule, not carbon dioxide. So carbon is changing chemically at all these different stages of the carbon cycle. Running through them, one thing is it's not a cycle exactly in the sense it's one big circle. No, it's a lot more complicated. Just like the nitrogen and the phosphorus cycle have lots of little cycles within them, the carbon cycle is not just one thing. There's many cycles that carbon can go through. So here are some examples. Usually for the carbon cycle, when it's explained to people, they normally start with the atmosphere. Carbon dioxide in the atmosphere could do a number of things. One is it can become absorbed into the water, just as dissolved carbon dioxide, absorbed into the ocean, absorbed into fresh water. Another thing that can happen once it enters the ocean is it can be used by the plants that live in the ocean. These plants are called algae, single-celled, tiny plants that live in the ocean. And being absorbed by algae, then it can enter food chains. Some of it becomes this stuff called carbonate, which is a bit like carbon dioxide, and that can then be absorbed by shellfish. That's actually a really important part of the carbon cycle, although it's kind of like unseen by most people. The carbonate that's in shellfish eventually can get locked in. By locked in, I mean locked inside the earth. Because shellfish, when they fossilize, the substances forms calcium carbonate, chalk. You'll know what is chalk, but the shellfish that are fossilized, the kind of rock that's made, is called limestone. Limestone, which is just calcium carbonate in a rock form, is a huge pool of carbon. Massive amounts of carbon are locked up in the Earth's crust in the form of limestone. Way, way more than you have in the atmosphere as a gas. Some of the energy-rich carbon molecules from the algae sink to the bottom of the ocean, especially in shallow water bodies and in river deltas. That, having sunk to the bottom of the ocean, can also form over a really long time frame with lots of pressure and heat, can form fossil fuels. The oil deposits of the world are formed under bodies of water, or were formed under bodies of water, oil and natural gas. The coal deposits of the world were formed from plant biomass that lived on land. But they're both massive pools of carbon, especially our coal supply. There's hundreds of years still left of coal. Burning it would be a really bad idea, but it exists. So these are some of the different pools of carbon that exist in the carbon cycle. But of course, we can't ignore people, because we use so much carbon as fossil fuels, and we take the fossil fuels and turn them into carbon dioxide and use them as an energy source. We've become part of the carbon cycle. And because carbon dioxide is a greenhouse gas which can trap heat in the atmosphere, we've become part of factors that affect the climate of the Earth. So the human impact here is massive and could become much larger in future times. So this is what I want you to know about the carbon cycle in terms of actually writing it down for me for notes. The processes we have here, we've got CO2 in the atmosphere becoming plant biomass. Some of it goes into soil. Some of that goes into fossil fuels like coal and gas. These can be burned or returned to the atmosphere. Fossil fuels can be used by people. Some carbon dioxide goes into the water, enters aquatic food chains. Some of that goes into fossil fuel, some to shellfish, and that which gets into shellfish, some of it is used, some of it ends up being converted to limestone and locked deep in the Earth's crust. That's what I want you to know about those cycles in terms of actually writing them down. Hey there, so just continuing my discussion of the water cycle, I thought it would be kind of fun to bring this home a little bit. I took this video about a couple weeks ago by Hudson Bay Mountain. I was riding my bike on the side of the road, saw this. It's really pretty. So all we can see here, of course, is a farmer's field. I'd like you to notice, for one thing, where the rain's not falling. Rain is not falling on me. Started to fall on me a little bit, but it's really falling. It's really concentrating its fall on the mountainside, especially on that part of the mountainside that faces where the weather came from. The weather came from this direction and over the mountains, and the water is mostly being spilled on the mountain itself. So that becomes, it's important to the water cycle for a very major reason, important to understanding it for a major reason. Because of where we are, let's try to zoom in there. Here we are in Smithers. What this map here shows is a map of what's called a relative humidity. So in other words, how much water can fit into the atmosphere relative to the maximum. So your relative humidity is always going to be higher in tropical places where it's like really muggy because it's really warm and lots of water can evaporate into the atmosphere. It's always going to be higher. The relative humidity relative to what can fit in the atmosphere will be higher in the tropics. But that being said, it still does vary from place to place in a way that doesn't depend on temperature. What does it depend on? Well, you can well imagine it depends on how close you are to water. The closer you are to standing water, the greater the chances are for water to be evaporated into the air around you, and so therefore the greater the relative humidity. So this 90% figure right here is for this little that you see right there. It's for this point here off the coast of Haida Gwaii, about, 200 kilometers west of Haida Gwaii, a little bit north. You've got this spot right here with 90% relative humidity. If we go towards the inland, as soon as we're going over land, the relative humidity is less, 68%. But when you're in the mountains, it's still pretty high. Notice where we are. We're right next to the ocean right here. Let's go inland, and it just dove. Here, 36%. Let's go to the Okanagan, 27% relative humidity. I guess it's here, whatever. It's drier inland. It's drier inland because, well, you're just not as close to bodies of water. Within the water cycle, water is transported from standing bodies of water by evaporation towards land areas. Some of it will fall as rain on the water itself, but some of it will be transported inland. This water system, the weather system, by the way, has very high relative humidity. This is what's called a low pressure weather system. It's cloudy and it's rainy. Let's have a look at that. What this shows us here is that it has brought with it this clouds, and this low pressure area has brought a rain front. It's cloudy outside right now because of the low pressure zone that was brought by this weather system. That's been developing over the last few days. These areas of high humidity here, what happens with them is they encounter the coastline. And when they do that, when they encounter the mountains along the coastline here we have in BC, they rise. That wet air, warm wet air rising into cold air condenses, and that condensation falls as rain. So it's very humid in the water off here, okay? We're seeing, let's go back to humidity. There. It's extremely humid here. All right, 94% humidity. And somewhat humid here. But let's look at that. So let's look right here, 96% humidity there, 74% humidity there. Let's go now to precipitation. Where's the rain falling? Remember, this was very humid right here, but only, let's go back to metric. That ain't right. Only 0.2 millimeters of rain falling here in the next 3 hours versus here that had the lower humidity but is right next to the BC coast mountains. 0.4 millimeters of rain is expected to fall there. Going further inland, 0.8 millimeters, 1.1. The rain is falling on the mountains as the weather systems go inland that have high relative humidity in the air and that moist air rises into cool air, encounters cool air, it forms rain. So there is a kind of a little microcosm example for you of the water cycle as it applies to the BC coast. One thing I didn't really explore at all was, what about the Arctic? Well, of course, you're going to have different patterns going on with the Arctic, because when it comes to the Arctic, you have a lot of seasonal pack ice. So there's actually much lower relative humidity over this pack ice, and it's a lot colder. And the water within the Arctic is often getting locked up. When it falls, it's getting locked up as snow and then only melting seasonally. But you know what? I'm not going to go into that anymore, because I want to change pace a little bit here. I'd like to talk to you a bit about the carbon cycle. So I've shown you the carbon cycle, but what I've mentioned as well is that humanity, with using our fossil fuels, they've removed what used to be a kind of an equilibrium of carbon dioxide concentrations. They were staying stable for a very long time, but they're not anymore. There's a guy named Charles Keeling who was working in Hawaii in the 1950s. He decided that he wanted to measure carbon dioxide concentrations in the atmosphere. He chose Hawaii. Specifically, he chose a mountain in Hawaii because it was very far away from any kind of industrial activity. There are no big factories in Hawaii making doohickeys. It's a vacation spot. So being so far away from any major industry, the air, by the time it gets to Hawaii, he expected it would be very mixed. There would be nothing that would dominate it relative to anything else. He could look at the average, he figured, more or less correctly, he could be looking at the average change in the average carbon dioxide concentrations in the atmosphere. What he found surprised him. First thing was maybe less surprising is the zigzag pattern. The zigzag pattern is a seasonal pattern. In fact, it happens over the course of 1 year. It results from the fact that there's so much more photosynthesis that happens on land, and that there's so much more land, and that when photosynthesis happens, carbon dioxide is absorbed. When decomposition happens, carbon dioxide is released. Also, there's a lot more land that exists in the northern hemisphere than in the southern hemisphere. So when we're going down in carbon dioxide, that corresponds to a northern summer, when the plants in Siberia and other parts of the northern hemisphere are sucking carbon dioxide out of the atmosphere, and it bounces back the following, during the following winter into early spring. It's bouncing back. It's bouncing back because it's more decomposition that's happening, especially in autumn. Your rate of photosynthesis has gone down. The rate of carbon dioxide release starts to exceed photosynthesis, and it comes back up. But then photosynthesis kicks in, and again it goes down. The seasonal pattern can be explained by plants soaking up carbon dioxide and then bacteria or decomposers releasing it. But this trend also had to be explained. And the only evidence-based explanation for the increase in carbon dioxide concentrations is burning of fossil fuels. It's been found that what's called the isotope ratio in the carbon that has been emitted, that's been collected over the course of the years, it's changed in a way that leads scientists to conclude that all of this extra carbon dioxide entering the atmosphere really does come from burning coal, burning gas, burning oil. So who's doing that? Well, it's us. So this is a human-made change to the Earth's atmosphere. And we can see here, if you sort of imagines putting this forward, it doesn't look like it's a line, does it? It doesn't look like, here it maybe looked like a line, but if it was just a perfect line, it would have done this, but it's not. It's curving upwards, which obviously is not promising. When I was reading a webpage earlier today, and it said, talked about how bad it was that carbon dioxide had reached 400 parts per million. Well, now if you look at carbon dioxide concentrations on the surface of the planet. Like in this null school diagram, you see that there's nowhere that it's as low as that anymore. Whereas just a few years ago, carbon dioxide concentrations hit 400 parts per million. Now they're above 400 everywhere. This is actually a really cool map, again, like all the null school maps are. What this one is doing is it's showing carbon dioxide concentrations mapped on the Earth's surface. There's a lot going on here that bears being unpacked. One is that here we are, as we are in early spring, the melt has only just been happening. Plants are only just starting to photosynthesize, so carbon dioxide concentrations are quite high. There's a lot of decomposition happening in Siberia, releasing carbon dioxide. The plants aren't taking up very much of it yet. So right now, the Northern Hemisphere, Northern Canada, Siberia, have got the highest CO2 concentrations that you'll find anywhere, 430 parts per million. If you compare that with, say, the Southern Hemisphere, especially, say, the Amazon rainforest, where there's plenty of photosynthesis happening right now, they're sitting at 411 parts per million there. I think I even found there's 405 parts per million in the central Amazon, these great forests of the world. In the south, the photosynthesis is happening, and so they are removing carbon dioxide from the atmosphere. So carbon dioxide concentrations are not uniform, but they've gone up. It used to be a big deal for them to be at 400 parts per million, and now they're at 430 parts per million. This is all happening over the course of a human lifetime. And the big concern is, all right, well, what if that starts to have more impacts that continue over the course of our century? So I've got actually another video I'm going to show you, another me talking video with the whiteboard I'm going to show you in a bit. But I do want to show you a couple more things about climate change. It took a while to find it, but I'm back, and here's what I wanted to show you. What this shows you here is an example of one of the greenhouse gases. It's called a CFC. It's got carbon, hydrogen, and chlorine in it, but you don't need to worry about that. What you do need to notice is this. What we've got here are different kinds of electromagnetic radiation that are zooming towards a molecule. All right, let's wait for one of those, an infrared photon, to hit it. There. It's brought it into motion. It kicked that molecule into motion. It's making it moving. It's been excited by this. And now another photon, another infrared particle has hit it, and the molecule is vibrating. What the CFC is doing is it's showing its property as a greenhouse gas. Greenhouse gases are gases that, when they are struck by infrared radiation, absorb that energy and get excited. They move faster, their bonds shake, and when that happens, they can spread their motion, their energy, to other molecules in the air like nitrogen and oxygen. This has the impact of increasing the overall temperature of the air. This is what greenhouse gases do. CFC is just one, but carbon dioxide is another one. I'm going to show you this as well. Maybe this is a bit advanced for you. I don't know. But this here is that's what's called Earth's emission spectrum. What does that mean? Well, it means that there's always light from the sun striking the Earth. We know this much. The light gives us energy. It's called radiation. Now, if that energy from radiation was always being soaked up by the Earth continuously and none of it was ever escaping, then the Earth would just get hotter and hotter and hotter and hotter and hotter. But that's not what happens. Instead, what does happen is, yes, some of that radiation is then absorbed by the Earth, but then the Earth re-radiates it. It re-radiates it as something called infrared radiation, which is the same kind of like radiation that your wood stove will project towards you and make your face hot even if you're standing across the room. That's infrared radiation. What this shows right here is the different kinds, different wavelengths of infrared radiation that the Earth re-radiates back into space. Now, the thing is, these are all gases that can exist in the Earth's atmosphere, or that do exist in the Earth's atmosphere. Water, a CFC, ozone, another CFC, carbon dioxide, methane, nitrogen dioxide. These are all what are called greenhouse gases. Watch this. There. What this shows is that light that is in this range of energy that is radiated by the Earth back into space, carbon dioxide has the ability, the molecules of it have the ability to capture that energy and keep it in the atmosphere. Now, infrared radiation of this energy, this wavelength here, that doesn't happen. The CO2 can't capture that. Let's see what happens with water, because there's water in the atmosphere as well. Oh, look, water recaptures the infrared radiation that's in this wavelength area here. There's also methane in the atmosphere. It has an effect over here. Nitrogen dioxide, also a greenhouse gas. These four are the major greenhouse gases in our atmosphere. There's others, these CFCs right here. Collectively, what they do is they are taking that energy, recapturing that energy from that's being radiated out by the Earth. They're giving that energy a second chance. Instead of that energy being sent to space, it stays in the atmosphere and warms up the atmosphere even more. We need a greenhouse effect, but we don't need as much of a greenhouse effect as these gases are giving us. Well, which is to say that having these gases pumped into the atmosphere at higher concentrations than they've been in the past is causing the globe to heat up, the atmosphere to heat up. What are some effects of that? Well, one of them is sea level rise. I've got a little video I'm going to show you that maps out all the places of climate change, just another whiteboard video. But here's something that I think is very exciting. So let's look at this. These are people in Greenland. They decided that they wanted to, it's a video called Chasing Ice, and they decided they wanted to record what's called a calving event. And the calving event is when glaciers in Greenland, which is north of Canada, of course, they break off. Glaciers that are next to the ocean break off and slide into the ocean. And they recorded the largest known calving event ever that had ever been recorded. So this is ice here that fell as snow possibly thousands of years ago that is now breaking off from the Greenland ice cap and moving into the ocean. This is quite fantastic. I mean, these pieces of ice that you're seeing are the size of office buildings, and they're shattering and breaking apart and moving into the ocean. So pretty incredible to watch. Why is it important? Well, it's important because unfortunately it has a downside. Melting in Greenland and also melting in the much larger Antarctic ice sheet has the potential of raising the sea level considerably. Low-lying countries like Bangladesh with 165 million people, they can't really afford to have this sort of thing happen. Bangladesh is maybe a quarter the size of BC, and it has 165 million people. It's full of rich farmland. It's been a great place that supported human life for a real long time, and a lot of agriculture there. But the downside gets to be, all right, it's a giant river delta emptying into the ocean. There's the potential, the very real potential, that if sea level rises because of melting ice, that melting ice will raise the sea level in Bangladesh, among other places, and mean that tens of millions of people need to leave their homes. So that's one major downside to climate change. And another that you'll probably remember, that you might remember earlier from earlier this year, were the bushfires that were starting to impact Australia. Australia has always had bushfires. If you follow the news from year to year, there's bushfires there every year because it's a continent that's hot, where a lot of trees also grow in some other parts. And the trees, the eucalypts, are prone to forest fires. So you get bushfires, a lot of understory fires, but in this case, a lot of like crown fires where the entire forest burns down. Australia has been experiencing a massive heat wave and drought during the past decade, and as a result, the forests have been drying out. When you take dry conditions, combine them with heat, combine them with forests, with lots of the source of fuel, that's a recipe for forest fires. And what this little dynamic shows you right here is the location of forest fires that affected Australia earlier this year and late last year. So those are really some of the key points that I wanted to show you in the screen video on the topic of climate change. And just hang tight, and there's also the whiteboard lesson that I have you that maps out the locations of different climate change effects. Hey there, Science 10. So just continuing lesson 10, or lesson 8, I should say, human activity and climate change. So part of the notes for this is looking at where climate change is going to happen, or what the effects are expected to be of climate change in different parts of the world, and I provide for you a map to put these out, write these on too. So this really relates directly to your climate change project. I've written up notes up on the board that kind of show the locations of some of these problems that I'm also going to be outlining in your screen-based lesson. So here's where they fall out for different parts of the world. So looking at my coding here. So S just means it's a greenhouse source. That's part of the world where they're mostly coming from. X is your extreme heat effects. D is desertification. F is forest or forest fires, which can be a source for greenhouse gases. R means sea level rise. I means melting ice cap. A is ocean acidification. W is flooding, and H is hurricanes or extreme weather. A punchline I want you to take from this is that the effects of climate change are expected to be global. Very few parts of the world, with the possible exception in New Zealand, are expected to be unaffected. So from my knowledge, here's where I see these impacts happening. So if we look at North America, first of all, major source of greenhouse gas, forest fires, desertification, sea level rise, like in Florida, could be issues. Here's South America, ongoing forest loss, as well as desertification, could be an issue there. Africa, not causing the problem, but desertification and extreme heat events, as well as forest loss and fire as a source of greenhouse gases, a problem there. Here's Europe. Europe, of course, is also a source of greenhouse gases as an economically developed region, but it's got a lot of low-lying altitude places which are subject to sea level rise as well, and I could have put an X there for extreme heat events. Well, that's all relative. The Middle East, Saudi Arabia right here. I guess we could almost put down S for that because so much oil and gas comes from there, but desertification and extreme weather can affect this region as well. India, massive population, per capita basis, not a huge greenhouse gas impact. If you're living in India, you don't have the same prosperity and they don't have the same impact on the climate as we do here in Canada on a per person basis. Here's Southeast Asia, so forest loss in Indonesia, Australia, desertification, extreme weather. Here's China, huge source of greenhouse gases, China, but of course, how would it not be? It's a manufacturing hub globally. And we see here for Siberia, forest fires and also fires in the permafrost could release more greenhouse gases. So, a couple other things. the low-lying Pacific Islands, there's lots of little tiny island nations or microstates scattered across the Pacific Ocean. Many of those have an altitude no higher than even like 6 feet. With sea level rise, they may well become flooded, and the countries could actually just go entirely out of existence. And then ocean acidification. I put the A right there because that's where the Great Barrier Reef is. Some of the great coral reefs of the world are located in this part of the world. And lastly, I didn't want to stretch out Antarctica, so I didn't scale it the same way. This is kind of a map of Antarctica, an I for ice cap melts. So that, from my knowledge, is how these different problems related to climate change all map out.